Okay. So before we begin, are there some questions which you may have? Then I'll begin by answering some questions. Can everyone hear me and see the screen? Okay. Okay. So let's start. Since there are no questions, let's begin the lesson. So last time we discussed about integral domains and a little bit, and then quotient rings. And I alluded towards isomorphism theorems towards the end. So we saw one explicit computation, in fact. So qx mod x square minus 2. And we showed that that's isomorphic to q square root 2, assuming the first isomorphism theorem and remainders theorem. Yeah. So today we'll see the first isomorphism theorem and maybe remainders theorem sometime later. Yeah. So recall that if R is R an integral domain and S so if S is a subring of R containing so we are assuming subring contains one of R, yeah. So one of R, then S is an integral domain. Subring of an integral domain is automatically an integral domain because you take a non-zero element in this subring, it's still a non-zero divisor. Yeah. And then we gave a ring structure to R mod I. This was the construction of the quotient ring. So R mod I is called the quotient ring or quotient of R by the ideal I. And we had this quotient map from R to R mod I, the quotient ring homomorphism. So we saw that this is a ring homomorphism, and we in fact saw that this is surjective. Yeah. So this is indeed surjective. So, and in R mod I, the images of the quotient map or the elements of R mod I, one can denote it by A plus I, or you can denote it by Q of A, where Q is the quotient map, or A bar. So this last one is going to be the most used because it's most compact notation, and by definition of addition or multiplication, or if you like the fact that Q is a quotient ring homomorphism, we have that A plus B whole bar. So you look at A plus B as an element of R and then apply bar, which is same as applying Q, is same as A bar plus B bar. Yeah. And then A times B bar is same as A bar times B bar. So these are these are basically writing. These are the things we saw. I'm just writing it in this new notation which we are going to use. Okay. So this is something which we discussed last time. Let R be an integral domain, then Rx is the polynomial ring in R. Polynomial ring over R in one variable is an integral domain, and hence so maybe add this polynomial ring in any finite number of variable x1 to xn is also an integral domain. Also an integral domain. Yeah, because you just apply induction. Yeah, so once Rx is an integral domain, you adjoin another variable, you get Rx1, Rx2, and so on. And the idea is you just take two non-zero polynomials, then their leading coefficients, so their degree sort of adds up if you are in an integral domain. Yeah. So the leading coefficients, if you look at the leading coefficients, their product can't become 0. Yeah? So let fx and gx be elements of Rx, non-zero elements of Rx. Then fx is something like this: an x power n plus an minus 1 x power n minus 1 dot 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 a0 for some ai's in R with an not equal to 0. Yeah, so you can find such an n could be 0. Yeah, so then it's a constant, non-zero constant, but it need not be 0. And similarly, gx is some polynomial of degree m. So bm must be non-zero, then only is the polynomial of degree m. Yeah. So so if fx will look like this, gx will look like this for some n and m, and some a0 to an and some b0 to bm in the ring R. Then fx times gx. So we know how the multiplication works. Yeah. So it's so we have done this. So you can use the formula which we wrote down for polynomial ring, or you use your experience of handling polynomials from high school. No? So it becomes an times bm times x power n plus m plus some intermediate terms which are slightly more complicated to write, and then the constant term is also easy to write, is a0 times b0. But the main guy which is of interest is this guy. Yeah. So since R is an integral domain and an and bm are non-zero, these two together implies that an times bm is non-zero, and which implies fx times gx is non-zero. Yeah, so it's a non-zero polynomial since this coefficient is non-zero. Okay, so let me not circle this. Okay. So so of course R is an integral domain, and then Rx is an integral domain. The converse is also true. Rx is an integral domain implies R is an integral domain. Why is that?
R is a subring.
R is a subring. So we saw that, right? In the construction of Rx, we saw that there is a natural map from R to Rx, and then we can identify the image, a natural injective ring homomorphism. So we can identify R as a R with the image of this natural injective. So then R becomes a subring of Rx, and then you use this observation. If you have an integral domain, then any subring is also an integral domain. Okay, so this is fine. So now we will. So before going to structure theorem, let's study ideals in R mod I. So what are the ideals of this ring R mod I? So so ideals of R. So ideals of R mod I are actually in bijection with ideals of R containing I. Okay, so this I was missing. Yeah, so these are so there is a one-to-one bijection between ideals of R mod I and ideals of R containing I. Yeah, so maybe one can write down some example. This is a bit thick, so let me just thinner one. So maybe I'll just write one example. So for instance, this we saw in the case of Z and Z mod n. Yeah, Z and Z mod n. So we were understanding the ideals of Z mod n. So these corresponds to, so recall the ideals in Z mod n corresponds to are of the form Az mod nz, where A is a factor of n. Yeah, A divides n. Yeah. So A divides n means so and any ideal of Z is of the form of this ring Z is of the form Bz. Yeah. So if you are looking for ideals which contain nz, then it is precisely of the form. So this So if you want to look at ideals which contain NZ, so this is BZ such that B divides N. This is ideals of Z containing NZ. So of course, BZ, if B divides N, then BZ of course contains NC. Yeah, and conversely, if you have an ideal BZ which contains NZ, then that tells you that N belongs to BZ, in which means that N is a multiple of. Yeah, so this is precisely the description. Yeah, and then you can see it's obviously a bijection. Here also we are looking at all integers which divides N. Here also we are looking at all rather natural numbers which divides N, and here also we are looking at all natural numbers which divides N. Okay, so there is an explicit bijection. There is not like an existential statement. It's a very easy statement. The bijection is given by, so if you take an ideal J in R containing I, then remember J is a subgroup of R and it also contains I, so J mod I makes sense. So which by definition is QJ as well. So this is so first observation is J mod I is not just a subgroup of R mod I, it's actually an ideal of R mod I. So this is the bijection in one direction. So from ideals of R containing I, and so J is an ideal of R containing I, and you go to ideals of R mod I. Yeah, so this is the direction, J going to J mod I. Yeah, so this is the bijection in one direction, and for the other direction, let W contained in R mod I be an ideal of R mod I, that is. Then Q inverse W. Remember, Q is the quotient map. Yeah, so maybe I should just mention that here. Q is the quotient map from R to R mod I. Quotient map. Okay. So Q inverse W is again an ideal of R, and then this will give you the inverse map. So we will show that Q inverse W is also an ideal of R, and then we will show that these two are inverses. Okay, so that's how we will prove that there is a bijection between the set of ideals of R containing I and the set of ideals of R mod I. So J mod I, as we argued while stating the proposition, J mod I is closed under addition. It's actually a subgroup of R mod I, so this part is okay. So we only have to check product, yeah. So let R plus I and A be an element of R mod I, and A plus I be an element of J mod I. We have to show that this times the product of these two is in J mod I. Yeah. So A plus I is in J mod I. That means that A belongs to J. Yeah. So that is what precisely means that A plus I belongs to J mod I. J mod I by definition is consists of cosets whose representatives are in J. Yeah. And R is some element of little r is some element of R. Yeah. So these two together implies that RA belongs to J. Yeah, because A belongs to J and R is an element of the ring, and J is an ideal. So that tells you that RA belongs to J, and this implies that RA plus I belongs to J mod I. But RA plus I is same as R plus I times A plus I. And hence we have shown that the product of these this guy and this guy is in J mod I. So we have shown that J mod I is an ideal ideal of R mod I. Yeah. So it's an R mod I ideal. Okay. And then we do the other so we show that, so now we start with, yeah, so now we want to show that Q inverse W is an ideal of R for W an ideal of R mod I. And we also want to show that I is contained in Q inverse W. So this bijection will work only if this happens. Yeah, so maybe I should add it in the statement as well. And then Q inverse W is an ideal of R. So maybe I'll just write it here. Containing I. Okay. Okay. So this so of course Q inverse W contains I is obvious, right? Because we showed that a kernel of Q is I. Yeah. So Q inverse 0 is equal to I. Yeah. So and W is an ideal, so it of course contains 0. So Q inverse 0 will be contained in Q inverse W. Yeah. So this part is obvious. So this part is clear. Yeah, from the fact that I equals Q inverse 0. Yeah. So from there you get that I is going to be contained in Q inverse W. So the only thing one has to check is Q inverse W is an ideal of R. Yeah. So in fact, we'll prove something more general. So instead of a lemma, maybe instead of a claim, maybe let me call this a lemma. Yeah. So it will follow from this lemma. Yeah. So if we have a ring homomorphism from A to B of commutative rings with unity, and J is an ideal of B, J contained in B is be an ideal of B, then phi inverse J is an ideal of A. Yeah. So here Q is a ring homomorphism. It's actually a surjective ring homomorphism, but surjectivity is not important to say Q inverse W is an ideal of R. We only need to know that it's a ring homomorphism. And from there we can deduce that Q inverse W is an ideal. Yeah, so it's a direct consequence of this lemma. Yeah. So let's just stay. So we'll use this statement many times. So that's why I've sort of isolated this statement separately. So it works for any ring homomorphism. So let's prove that. So so we want to show that Q inverse J is an ideal. So we have to show that it's closed under addition and it's closed under multiplication by elements of A. So Q inverse J of course is contained in A. So let A1, A2 be two elements of Q inverse J. So what does that mean? That tells us that sorry, phi inverse of J, not Q. Q was over. So A1, A2 are two elements of phi inverse J. So that tells us that phi of A1 and phi of A2 are in J. So that tells us that phi of A1 plus A2 is in J. Yeah. So that tells you that A1 plus A2 is in phi inverse J. Yeah. So straightforward statement. And similarly, scalar multiplication is also okay. So let's take an element R in A and A in phi inverse J. Then if R is in A, then of course phi R is in B, because phi is a map from A to B. Yeah, so phi R is in B and A is in phi inverse J. That tells you that phi A is not just an arbitrary element of B, it lands in the ideal J. Yeah, but J is an ideal of B, so that tells you that phi R times phi A is in the ideal J. So and then you use the fact that phi is a ring homomorphism. So this is where we use that phi is a ring homomorphism. It's a ring homomorphism. So so that tells you that phi of RA. So phi R times phi A is same as phi of RA. So phi RA belongs to J. And that tells you that RA is in phi inverse J. Yeah. So we started with an element R in A and A in phi inverse J, and we concluded that R times A is in phi inverse J. So that tells you that phi inverse J is an ideal of A. Yeah. So now so that
in the lemma we don't need unity.
Sorry, I 1 second. I think my volume is low. Yeah. Can you repeat the question, please?
Sir, in the lemma we don't need unity.
Yeah. But ideals I have defined only for rings with unity.
Okay.
So I don't want to worry about otherwise. Okay, you don't need, I mean, this commutativity also you don't need in some sense if you want to keep track of left, right ideals and so on. But let's not worry about working in complete generality. Let's try to understand this subject in this form. So this is the most useful form anyway. Yeah, and when you are trying to do non-commutative rings, the ideas are same. You just have to be a little careful about whether you can change the order of multiplication. Okay. Okay. Any other question before we go on? Okay. So there are no questions. So what we have shown so far is that both J mod I is an ideal and Q inverse W is an ideal. Yeah. So now we will show that the two maps which we defined, J going to J mod I, and from set of ideals of R containing I to set of ideals of R mod I, and the other map W going to W Q inverse W from ideals of R mod I to ideals of R containing I. This is these are inverses to each other. Yeah, and then we'll be done. Yeah. So let's start with an ideal of R containing I. Then of course J mod I is an ideal of R. We just have to check that this happens. Q inverse J mod I gives you J back. Yeah. So why is that? So we just have to prove this equality, and that's done in the bracket. Yeah. So if A belongs to Q inverse J, then of course that means that A plus I belongs to J mod I. Yeah. So that means when you apply Q to A, which is same as taking A plus I, belongs to J mod I, which implies A belongs to J. Yeah. And this is reversible. So if A belongs to J, then of course A plus I belongs to J mod I, and that precisely means that A belongs to Q inverse J mod I. Okay. So these are both, both implications are true. Similarly, if we start with an ideal in R mod I, we apply Q inverse W and then go mod. So we know that Q inverse W is an ideal of R. Can be an ideal of R mod I. So there is a correction here. Then Q inverse W we know is an ideal of R which contains I. So we can take this, we can mod it out by I, and we want to show that this this is equal to W. So we want to show this equality now. Yeah. So we want to show this equality now. Yeah. So you take some element in W, for instance, A plus I. So A plus I belongs to W if and only if A belongs to Q inverse W. Yeah. I mean, because Q inverse of A plus I is, so if you take Q inverse of A plus I, it will contain A, yeah, because Q of A is precisely A plus I. And conversely, if A belongs to Q inverse I, then Q inverse W, then A plus I belongs to W. So both implications are true. And similarly, A belongs to Q inverse W if and only if A plus I belongs to Q inverse W mod I. Okay. Okay. Any questions? So we have shown that these two maps, J going to J mod I and W going to Q inverse W, these are inverses to each other. Yeah. So these two statements says that they are inverses to each other, and hence we have a bijection. Okay. So this is just verification verification statement. There is no I mean, there's in some sense there is no trickery, no depth, no computation, anything. Yeah, it's just verifying it. Okay. So let's move to. So now we will go to isomorphism theorem. Okay. Yeah. So maybe I can. I hope it's visible. This side, left side is visible. Okay, maybe I'll expand it a bit. Let me just make this observation first. So this is something which we didn't prove, but this is an obvious statement. If you have two ring homomorphism phi and C, then their composition is also a ring homomorphism. Yeah. So meaning you have seen this for groups, I hope. If you have C is a group homomorphism from G to H and C is a group homomorphism from H to K, then C composed phi is a group homomorphism from G to K. Yeah, so the same thing holds for rings as well. So you, I mean, for groups you have already checked for addition. So here you'll have to check for multiplication, but straightforward. Yeah. So I'm not going to. So should I do this? Okay. So. So I mean, all you have to check is that C of. So you have to check C composed phi behaves well with respect to multiplication. Yeah, so maybe in this space is enough to do it. So let me just do it. C composed phi of A times B, A1 times A2, let's say, is same as C of, so phi is a ring homomorphism, so it's same as phi of A1 times phi of A2. Yeah, so here we are using that phi is a ring homomorphism, but C is also a ring homomorphism. So I don't know where did this come from. Yeah. Okay. So this tells us that C of phi A1 times C of phi A2, since C is a ring homomorphism, which is same as C composed phi of A1 times C composed phi of A2. So if all the three rings have different different looking operation, this two statement will look weird, but this is what it is. Yeah, but formally that is how one should write it. So if you feed it into a computer, that is how the computer would write it. If you give A, B, C different ring operations, but now I hope we have mastered this ring homomorphism, so we won't give different operations to different rings. From the context, it's clear where the ring operation happens. Yeah. So, for instance, here it happens in A, here it happens in B, and here it happens in C. Yeah. Okay. So now coming to isomorphism theorem. So this is our first isomorphism theorem. So let phi from A to B be a surjective ring homomorphism then the induced map phi bar from A to kernel phi, A mod kernel phi to B, which sends A bar. So A bar is the image of an element A in A mod kernel phi. Yeah. So A bar is same as, so maybe A bar is same as, so A bar is same as A plus kernel phi. Kernel phi, remember, is an ideal of A. Yeah, so it's this quotient. So A bar goes to phi A. So this map is an isomorphism. This is the statement of the theorem. So there are a couple things about this theorem. First of all, it's not clear that this is a ring homomorphism. So first, so maybe you can say there exists a ring homomorphism with some property which makes it into a, or you can explicitly describe this ring homomorphism, but one will have to say that this is a well-defined map. So we'll see all that, yeah. So there is a ring homomorphism. So phi is be a surjective ring homomorphism, then A mod kernel phi is isomorphic to B. That is what the first isomorphism theorem says in some natural way. And natural way means that A bar goes to phi of A. This is the map. Okay. So first isomorphism theorem is a special case of this next proposition. So sometimes this next proposition is called the first isomorphism theorem. They are all related statement. Okay. Sorry, so this was not visible. So they are all related statement. Yeah. So let phi from A to B be a ring homomorphism. So we will see that we'll see the proof of first isomorphism theorem as a corollary to this proposition, which I'm going to deep now. Yeah. So let phi from A to B be a ring homomorphism, and K be some yeah. So I didn't write what K is. So and K contained in kernel phi be an ideal of A. B and A ideal. A ideal means ideal of A. Yeah. Then there exists a ring homomorphism phi bar from A mod K to B such that phi bar composed Q is equal to phi. Yeah. So this is so phi bar is a map from A mod K and Q is the map from A to A mod K. Yeah. So so this diagram should commute. So pictorially, A to B is, so this is a commutative diagram is what you would see in many algebra books or in future algebra courses. So this is a commutative diagram. This is, yeah, so maybe, I don't know, this diagram commutes. So yeah, it's not clear why this is called a commutative diagram, but when the diagram is more complicated, it will be clear why this is called. So this is there is nothing commuting here, but when you have a square or rectangle, then it is actually something about commuting of maps. Okay, but anyway, even this is called a commutative diagram. Okay, so what precisely commutative diagram means is that this happens in this context. Yeah. So so you first apply Q and then apply phi bar. It's same as phi. Yeah. So the content of the theorem is you can find a ring homomorphism this such that this happens. Okay. That is the statement of this proposition. Is the statement clear? So so since it's an important statement, and so I'll take a pause. So have you seen this statement in the case of groups? First isomorphism theorem. In group theory, did you see this statement?
Yes.
Okay. Okay. Good. Okay. Then this shouldn't look very unfamiliar. Yeah. It's just that in group theory you would want this. So K to be something normal in A, normal subgroup of A, and then this will work. Okay. But here you want this K to be an ideal of A. Okay, so in particular, if K equals kernel phi, then phi bar is injective. Yeah, so this is the second part of this proposition. So here we are taking K to be some subset of kernel phi, which is a ideal of A. Now, of course, if so K can be equal to kernel phi because that itself is an ideal. Then you can also say that phi bar is injective. Yeah? So we'll see next. We'll see the proof of this proposition. Yeah. So I've already told you what phi bar should look like in the statement of first isomorphism theorem. Yeah. So phi bar is A bar should go to phi A. Yeah. So, but one has to define say that this is well defined, right? Because we are looking at a coset and we are defining the map in terms of a representative of a coset. Yeah. So if we are given two different representatives, then we have to show that the definition it leads to the same target. Yeah. So remember this A bar means A plus K. Yeah. If you like. So I'm using this shorthand A bar, but I'm adding this so that there is little confusion. Okay, so phi bar is so first step is to show phi bar is well defined. So let A bar equals B bar be two elements of A mod K for some A B in A. So A bar equals B bar means A minus B belongs to K. Yeah? So A plus K equals B plus K. Yeah? So the two cosets are same if the difference of the representative lies in K. Yeah, so A bar equals B bar implies that A minus B is contained in K. It belongs to K, and we know that that is contained in kernel of phi. So that tells us that phi of A minus B is 0 in the ring B, and that tells you that phi of A equals phi of B in B. Yeah, so hence phi bar is well defined. Okay. Any questions? Okay. So once you have that phi bar is well defined, this is the only check one has to do, and then the rest is sort of follows. Yeah. So now phi bar. So we have to still check that phi bar is a ring homomorphism. Those things follow immediately from the fact that phi is a ring homomorphism, and the fact that this composition holds is sort of by definition. Yeah. So phi bar is a ring homomorphism. So let's check that. So phi bar of A bar plus B bar, where A bar and B bar are elements of A mod K. By definition, this is same as phi bar. Yeah, so somehow here it should be phi bar. Yeah. So A bar plus B bar is same as A plus B bar. Yeah. Some observation which we made earlier. Yeah. So in this A bar B bar notation is same as A plus B bar. So phi bar of A bar plus B bar is same as phi bar of A plus B bar. But by definition, phi bar of A plus B bar is same as phi of AB, A plus B, yeah? Which is equal to phi A plus phi B. Okay, so this is because phi is a ring homomorphism. Phi is a ring homomorphism. Okay, and so what we have shown is that phi bar of, yeah, so and of course phi bar of A bar plus phi bar of B bar is also phi of A plus phi of B, because phi bar of A bar is phi of A and phi bar of B bar is phi of B. So we see that these two guys are same. Yeah, so that tells you that phi bar behaves well with respect to addition in A mod K, and similarly phi bar it behaves well with respect to multiplication. So phi bar, yeah, so we have forgotten this guy. Yeah, so phi bar of A bar times B bar is equal to phi bar of AB bar, which is equal to phi of AB. Yeah, by definition of phi bar. But phi of AB is same as phi A times phi B, and phi A is same as phi bar A bar, and phi B is same as phi bar B bar. So that tells you that phi of A times phi of B is phi bar of A bar times phi bar of B bar. So we get that these two are equal. So we get that these two are equal. Yeah. Which proves that phi bar is indeed a ring homomorphism. So we have shown existence of a ring homomorphism from A mod K to B. Yeah. So that's what we have done so far. So next we want to show that phi bar composed Q is equal to phi, and then we will show this in particular statement. Yeah. So now you take an element A in A, and so phi bar composed Q and phi both are maps from A to B. Yeah. So phi bar composed Q is first apply Q and then apply phi bar, and phi is the original map given to us. We want to show that these two are same. So we evaluate it at an arbitrary element of A. So given an element little a of A, capital A, we apply this phi bar composed Q of A. So here Q is, recall Q is the map from A to A mod K, yeah, the quotient map. Yeah, so phi bar of composed Q of A is same as phi bar of A bar. So A bar is, remember, is same as A plus K in this proposition. Yeah. And phi bar of A bar by definition is same as phi of A, and definition of phi bar. Yeah. So we get that phi bar, so see phi bar composed Q is same as phi for arbitrary element of A. So that tells you that the two maps must be same. Yeah. So you evaluate it at any arbitrary element, you get the same answer. So that tells you that phi bar composed Q is same as phi. Okay, so that proves the first half of the theorem proposition. The last sentence is, if K is equal to kernel phi, then we want to show that phi bar is injective. Yeah. So to show phi bar is injective, it's enough to show that the kernel of phi bar is 0. Yeah, it's the 0 element of A mod K. Yeah. So let A bar be an element of A mod K, and such that phi bar of A bar is 0 in B. Then we want to show that A bar is actually the 0 element of A mod K. Then we can conclude that phi bar is injective. Yeah? So phi bar of A bar is 0 in B. What does that mean? That means phi of A is 0. Yeah, because that is the definition of phi bar A bar. So phi of A is 0. That tells you that A actually belongs to the kernel of phi. So belongs to K, which is equal to kernel of phi. So here K is equal to kernel of phi. So if A is 0, that means A belongs to kernel of phi, which is same as K. So if A belongs to K, that tells you that A bar is 0 in A mod K. Yeah. So hence kernel of phi bar is 0. Yeah, which is same as saying so this is another way of saying that phi bar is injective. Yeah. So this I guess you have seen it in group theory that ring homomorphism, group homomorphism is injective if and only if the kernel is trivial. So the same, that is what we are using. Yeah. Phi bar, remember, is also a group homomorphism. So we are not really, we don't need a corresponding statement for ring formally. Okay. Any questions? So I think this is all on in this page. So I can minimize this. and show you the whole thing. Okay, so somehow when I write the whole lecture, things go a little too smooth. So I don't know if this is a good idea. So I feel like maybe I move a little, I'll go a little faster. And there's more interaction, the chances of learning is a bit better. So I don't know if I should write in advance or not. Maybe I'll put up a poll and you can let me know. So if there are no questions, I'll get to this half of this. So we'll proceed after a short break. Yeah. So let me just take a short break here. Okay, so about that chat question, you have to. So in the homework, since this we have done just today, in the homework you should, and quotient rings were covered only this week. In the homework, you shouldn't use that result about quotient. It's probably easier to just directly prove that statement about ideals in Z mod and Z. Okay. So now the proof of first isomorphism theorem. So recall this first isomorphism from this left panel. Phi is a surjective ring homomorphism from A to B. Then phi bar from A mod kernel phi to B, sending A is an isomorphism. This map A bar going to phi A. Yeah. So by proposition, which we proved, this proposition on the left, phi bar from A mod kernel phi to B is an injective ring homomorphism. But we are given that phi is surjective, so that tells you that phi bar and we know that phi bar composed Q equals phi. So phi bar is also surjective. So anything which is in the image of so the image of phi bar is going to be same as image of phi by this formula. Yeah. So since the image of phi is B, image of phi bar is also B, and hence phi bar is not just an injective ring homomorphism; it's also a surjective ring homomorphism, which tells you that phi bar is an isomorphism. Yeah. So this statement, the first isomorphism theorem, is basically a special case of this proposition. Okay. Any questions? Okay. So no questions. So yeah. So in that example, maybe. So in yesterday's example, Qx mod x square minus 2. So we gave a map from Qx to Q square root 2. Yeah, Q adjoint square root 2. The subring of the field of the real number which contains Q and square root 2, smallest sub. And we saw that the kernel is precisely x square minus 2, the ideal generated by x square minus 2. So Qx mod x square minus 2, the ideal generated by x square minus 2, is isomorphic to the image, which is Q adjoint square root 2. Okay, so this is so now you know this part of the proof. The only part remaining is remainders theorem. So for Qx over Q, you probably know the remainders theorem. So that's not. So that is also okay. So that proof is more or less complete now. So then there is the second isomorphism theorem. Like in group theory, you have three isomorphism theorems. Similarly, for ring theory or for module theory as well, in which we'll see later on, we'll have three isomorphism theorem. So like in abelian groups, the three isomorphism theorems are best written. Similarly, in modules case, the three isomorphism theorem will be the best written one. And you have to put in certain hypotheses, some artificiality for rings or for general groups. Like you have to talk about normal subgroups. Here you have to talk about ideals and so on. So here, so let R be a commutative ring with unity, S be a subring of R, and I be an R ideal. Then S plus I is a subring of R, S intersection I is an S ideal, and S plus I mod I is isomorphic to S mod S intersection I. So S plus I, remember, is a subring of R, and it contains I. So left hand side makes sense. So it contains I, and hence will be I will be an ideal of S plus I. So this left hand side as a quotient ring makes sense, and S intersection I is an S ideal. So this right hand side also as a quotient ring makes sense. Yeah. So these two are isomorphic as rings is what I should say. As rings. So these two are isomorphic as rings. So this is what second isomorphism theorem is. So all this second and third isomorphism theorem, they are a corollary of the first isomorphism theorem. Okay. So it follows more or less from the first isomorphism theorem. So we'll give the proof of this. Yeah. So the isomorphism part is the corollary. The rest one has to just check. So let's just check S plus I is a subring of R. So let's take two element alpha and alpha prime in S plus I. So by the way, what is S plus I? So it's a subset of R, and it contains elements of the form R plus A, where little r is in S and A is in I. Yeah. So it's similar to the notation I1 plus I2. Okay. So let's take alpha and alpha prime in S plus I. Then alpha is R plus A for some R in S and A in I, and alpha prime is R prime plus A prime for some R prime in S and A prime in I. Yeah. So we get that alpha plus alpha prime is so we have to show that their sum and the product lies in S plus I. Yeah. So their sum is R plus R prime plus A prime. So it lies in, so the first term lies in S and the second one in I. So this belongs to S plus I. Yeah. So sum is there is nothing, and even in the product you just have to arrange. So if you take the product, then R times R prime is something which lies in S because S is a subring. Yeah. And R prime are in S, so their product lies in S, and the rest will have one term of I. Yeah. So for instance, A. So you just expand it, so you'll get A R prime plus. So R times R prime you have done, then A times the remaining part you do, A times R prime plus A prime, and then you have R times A prime, which is missing. Yeah. So the remaining three terms are of course in I, because I is an ideal. So this A is in I. So this time in A times anything is in I, and A prime is in I. So R times A prime is in I. So their sum is in I. Yeah. So alpha times alpha prime, again you can write it something as something in S plus something in I. So this is also is in S plus I. So this is in S plus I. Yeah. Maybe I can make it brighter. This is in S plus I. Okay. So we have seen. So now we have that S plus I. I was a little worried whether I unmuted myself. Yeah. So we have seen that S plus I is a subring. Next is S intersection I is an S ideal. So that follows from the lemma which we proved. Yeah. So S intersection I is same as I inverse I, where this little I is the inclusion map. So S is a subring of R. So we can think of it, we can write it as an inclusion map I from S to R. And inclusion map is a ring homomorphism. If S is a subring of R, then I inclusion map is a ring homomorphism. So in particular, we get that I inverse this inclusion map I inverse capital I is actually an ideal of the domain, which is S. But I inverse I is by definition S intersection I. Yeah. So S intersection I is an S ideal by lemma. And the lemma which was proved in the middle of a proposition. Yeah. Where we gave the bijection between ideals of R mod I and ideals of R containing I. Okay, so S mod I, S intersection I is an ideal of is an S ideal. So now the objective is to use this first isomorphism theorem. Yeah. So we want to give a map from a ring A to B, surjective ring homomorphism, and then compute the kernel and so on. Yeah. So this is the map. So to say S mod S intersection I is isomorphic to S plus I mod I will give this this ring homomorphism. Yeah. So S is a subring of S plus I. So we have this inclusion. Inclusion is a ring homomorphism. So inclusion to R is also a ring homomorphism. Of course, inclusion to S plus I will also be a ring homomorphism. And we have I is an ideal of S plus I. Now, so we can look at the quotient map, which I denoted by Q here. So this is also a ring homomorphism. So we look at the composition of these two. Yeah. So phi is composition of this I and Q. So this composition of two ring homomorphism, as we observed, is a ring homomorphism. Okay. So phi is a ring homomorphism, and next thing I want to do is check that phi is surjective. Yeah. So I think this next statement is about checking. I don't know why. Yeah. Now I can move it here. So we'll check that phi is this ring homomorphism is surjective, and then we'll compute the kernel and show that the kernel is S intersection I, and then then the statement will follow from first isomorphism. Okay. So let's take alpha in S plus I mod I. Then we want to show that alpha is phi of something in S. Yeah. So what is alpha? Alpha is an element of S plus I mod I. That means some people are yelling outside. So alpha is some element of S plus I mod I. So alpha we can write it as R plus A bar. Yeah. So this is where R is some element of S, A is an element of I. So I mean, if you like, you can also write it as R plus A plus I if you want to use the coset notation. Yeah. But as I said, it's much compact to use this bar notation. Yeah. So alpha is of this form, where I is some element of S and A is some element of I. Yeah, because S plus I, elements of S plus I precisely looks like that. So alpha, but A belongs to I. Yeah, so R plus A bar is same as R bar. Yeah, R plus A minus R is equal to A, which belongs to I. So alpha is also equal to R bar, which means so alpha is equal to R bar means alpha is a phi of R. Yeah. What do you do? So this so you think of R is an element of S. The inclusion will tell you R is an element of S plus I, and then you apply Q, then you get alpha. Yeah. So this is precisely what we are doing. First applying I and then applying Q to get R bar. Yeah. So R bar is exactly applying Q directly, or you can think of it as inclusion followed by Q. Yeah. So that tells you that phi is surjective. Yeah. So we have that this ring homomorphism which we cooked up is actually surjective. And now we have to calculate the kernel of phi. So if we show that the kernel of phi is S intersection I, then by first isomorphism theorem, S mod S intersection I is isomorphic to S plus I mod I. Okay. Any questions? Okay, so if there are no questions, let's move to the other.
One question in the beginning, while proving that S plus I is a subring, we use the commutativity here. So is it not true for a non-commutative case?
You'll have to assume I is a two-sided ideal. So if you assume I is a two-sided ideal, then there is no issue. Yeah.
Okay, sir.
Okay. So quotient you can take only if it is a two-sided ideal. That's why. Okay. Quotient, and then you want a ring, then you have to make sure it's a two-sided ideal. Okay. Yeah. So let's get back to the proof. So we have shown that phi is surjective. Yeah. So for some reason I can't make this smaller. Okay. So I'll just wait a little bit. Yeah. So that you have this. Yeah. So hence phi is surjective, and this doesn't become any more small. Okay. So now we compute the kernel of phi. Yeah. So the claim is that the kernel of phi is S intersection I. Yeah. So that also is easy to check. So remember, phi is this inclusion mod this quotient. Yeah. So of course if you take something in alpha in kernel of phi. So I mean, if you look at the diagram, then I mean there is a proof using elements, but you just think about it. Kernel of Q is I. Yeah, and then of course if you are looking for kernel of I Q composed I, then it has to be something in S, so it has to be S intersection I. So intuitively it's clear, and then you just look at so you just write down that proof in terms of elements. So once you have guessed this, let alpha be in kernel of phi. That tells you that phi of alpha is 0. But what is phi of alpha? So alpha is so first of all, of course, phi is a map from S to S plus I mod I. Yeah. So alpha is in S, and phi of alpha is 0. But what is phi of alpha? It's alpha plus I. Yeah. So you think of alpha as an element of S plus I, and then go mod I. Yeah. So that is alpha bar or alpha plus I, whatever you want to. So this tells you that alpha plus I is 0 in S plus I mod I. Yeah. And alpha is some element of S. So that tells you, so alpha plus I is 0 means alpha must be in I. Yeah. That is what alpha plus I being 0 means. So alpha is not just in S, but it's also in I. So alpha belongs to I intersection. Yeah. So that tells you that kernel of phi is contained in S intersection I. You have written I intersection S. And the converse is obvious, right? So if you take something in S intersection I, anything which is in I will go to 0 in S plus I mod I. Yeah. Then of course phi alpha is going to be 0. Yeah. So the other inclusion is obvious. Because anything in I goes to 0 under phi. Yeah. So that tells you that that the kernel because I is equal to kernel of Q. That is the reasoning. So that tells you that the claim is indeed true. So kernel of P is equal to S intersection I. Hence, by first isomorphism theorem, we have this result. I'm trying to draw a box. Okay. Okay. So any questions? Okay. So maybe so there is also third isomorphism theorem, which is also not difficult, and so we will begin next lecture on Tuesday with third isomorphism theorem. Okay. So any questions before we disperse? So this is all I wanted to say today. So you can ask your questions now. I'll be here for 5 minutes. If you don't have questions, you're free to leave.
Excuse me, sir.
Yeah.
Sir, in the previous class notes, at the last, give examples.
Mm-hmm.
Sir, I want to understand that fifth example once more.
Yeah, I should have gone over that examples. Yeah. Okay. So, okay, so I'll go over it in the next class as well. But let me just recall. So, what was the exam? Can you just recall what was the example?
Sir, it was ZX quotient 2 comma x square minus 2 ZX.
ZX quotient ideal generated by 2 comma x square minus 2. Yeah.
And then Z.
Yeah. So that is this notation means is the ideal generated by 2 and x square minus 2. Okay. So this. Yeah. So okay, if you like. But we'll soon abbreviate to this thing. Yeah. So so what is the statement I made is this is isomorphic to Z mod 2Z adjoint X. Sorry, maybe the statement I made was that this is isomorphic to this Y mod Y square. Yeah. So first, so this will, so this uses, so this uses third isomorphism theorem. Yeah, so maybe you will see the application of third isomorphism theorem before seeing the third isomorphism theorem, like in the second isomorphism theorem. So you have two ideals here. I is ideal generated by 2 and x square minus 2. So one should put Zx, but this is the people use this as the notation for ideal generated by these two in Zx. Yeah, and then there is a smaller ideal which is let's say J, which is the ideal generated by x square minus 2. Yeah, so this of course is contained in I. Yeah,
Yes.
so yeah, so the statement is that and maybe there is another, so I think I'll need the smaller ideal this. So this is also a smaller ideal and this is contained in I. Yeah, so I need this ideal actually rather than J. Yeah, so the third isomorphism theorem says that R mod I, so R is Zx. Okay, maybe I'll write it here, R. Yeah, so R mod I is R mod I is isomorphic to, first you take R mod K, yeah, and then you take I mod K. Okay, so I mod K will be an I is so I remember R mod K R mod K is a quotient of R. Yeah, so ideals of R mod K are in bijection with the ideals of ideals of R containing K. Yeah, so so I is an ideal of R containing K. So I mod K is an ideal of R mod K. Yeah, so this is the this is one of the first statement we proved. Yeah, so once we have, since I mod K is an ideal of R mod K, we can take this quotient. Yeah.
Yes.
And this will be a ring. And the third isomorphism theorem says that these two are isomorphic. Okay. So now you just apply this third isomorphism theorem here blindly. So this tells you that Zx mod 2 comma x square minus 2, this ideal, is isomorphic to Z mod 2Z, sorry, Z, sorry, not, it's a little bit more. Zx mod 2, the ideal generated by 2, over so K here, right? And this here I mod, let me just put I mod K. Yeah. But what is Zx mod 2? Yeah. So this, yeah, so there is a little more than third isomorphism theorem. So you can, so this is same as Z mod 2, 2Z polynomial ring in X. Yeah. Okay. So maybe so something one has to check. So this follows from first isomorphism theorem. So you of course have a map from this to this, yeah, ring homomorphism. What is that? So you take a polynomial f with coefficient in Z and you look at it mod 2, yeah. So you'll get a polynomial in Z with coefficients in Z mod 2. And this is going to be a surjective ring homomorphism, and the kernel is precisely polynomials which are multiples of 2, which are divisible by the number 2. So the idea, so the kernel of this map phi, so kernel phi is the ideal generated by 2. Yeah. So 2Zx if you like. Which okay, so that tells you that Zx mod 2 is isomorphic to Z mod 2x. Okay, so this will say that the numerator here is isomorphic to this guy, and under this isomorphism 2 will become 0, and what you will get is x square minus 2. But x square minus 2 in this ring, yeah. So one should write it as 2 bar instead of x square minus 2, yeah. But what is x square minus 2 bar? So 2 bar is same as 0. Yeah. In Z mod 2. So this is isomorphic to Z mod 2Z x mod x square. So I had written y square. So you just change variable and the name of the variable. So 2 bar is same as 0 in Z mod 2. Yeah. So that tells you that this is same as this. Does this make sense?
Yes, sir.
So yeah, so we'll work out this example maybe again now. So some people may have left. Yeah, more than half the class left. So we'll work out this example after the third isomorphism. Okay. And maybe remind me of doing one more example, the other example as well. With,
So 5 comma x squared.
Yeah, 5 comma x squared. So both are similar. So we'll do both examples. Okay. Okay. So maybe it's time to leave. Okay. So let me just pause this recording.